Well, hello everyone. Thank you for tuning into my virtual presentation. My name is CrystalWespestad, and I'll be giving an overview of my master's presentation called Assessing Perception of GIS Visualizations Depicting Differential INSAR Ground Deformation Measurements. So I'll just point out quickly that throughout my presentation, I'll be keeping track of where we are in the banner along the left side there. And I'd like to start with the purpose of this project. The detection and monitoring of geohazards is a matter of public safety. Geohazards are deformations of the land surface that are potentially dangerous or damaging. Some occur naturally, such as earthquakes and landslides, while some are more human-induced, such as sinkholes from oil extraction complications, as shown here, or overdrawing of groundwater for farming. That is what partially caused the 9 meters of land subsidence or downdropping between 1925 and 1977 in California in this picture on the right. Geohazards can be dangerous to infrastructure, buildings, the environment, and people themselves. Therefore, the occurrence of these geohazards must be effectively communicated to the public, which is the main focus of this project. If the complicated analyses used to detect and measure geohazards cannot be demonstrated in a simple manner, the science does not serve its purpose. Sometimes these ground deformation features can be so remote or so large that they are not easily seen from the surface. But satellites allow us to detect them using radar technology, which allows for frequent high-accuracy elevation measurements. This satellite is Sentinel-1 from the European Space Agency, and it is the one I use for my radar analysis. The specific type of radar technique I used is called Densar, or Differential Interferometric Synthetic Aperture Radar. I'm going to take a minute here to talk about exactly how this technology works. Densar remotely measures changes in elevation over time. In order to make radar measurements, a satellite emits microwaves towards the Earth and records the waves that bounce off the ground and return to the satellite. It does this again, observing the same ground location on a later orbit around the Earth from the same point in space. If there's any difference between the observed wave signals, this is interpreted as a change in the ground surface. And the waves that reflect back to the satellite will be slightly different because they had to travel slightly altered distance. This difference can be very accurately measured at the centimeter scale. When I show you figures in the rest of my talk, you can think of them as change maps, displaying the alterations of the ground surface between the two satellite observations. So I focused my analysis on a study area suggested by my technical advisor, which is known to have ongoing land deformation. It lies within an active oil field in southeast New Mexico. I later narrowed my focus to a small study site in this area. So here's a zoomed in map of that Densar analyzed area, so you can see why I chose this smaller study site. This rainbow image is that change map I just referenced. It's called an interferogram. I chose this small study site because it displayed evident deformation centers, which are concentrated areas of ground deformation that show up as little rings of color in the interferogram, similar to rings around a hill on a topographic map. Now I'd like to outline the methods of my project for you. I won't go into further detail of the Densar analysis because that would take far too long, but it is important to note that the measurements for this analysis are by default given in units of phase residuals. I converted these to vertical Z values in units of centimeters so they'll be more intuitive in my visualizations. This conversion process is called phase unwrapping. The innovative part of my project, though, was the exploring different ways to visualize this ground deformation data. I produced 3 types of figures: 2D maps, cross-section graphs, and 3D videos. And within each of those types, I designed 3 subtypes. The first one is raw deformation values displayed as is, then difference from the average deformation, and finally as cumulative deformation over time. I evaluated the effectiveness of all of these visualizations using a preliminary online survey developed using Qualtrics, and then these results were graphed and analyzed. Oh, and also I hope graduation is the last step, really. Now I'll walk you through the visualizations I made I used in my survey. Thank you again to all of you here who took it. I know several of you did. This first one is the default visualization of Densar, the interferograms. As you can see, they are measured in color scale of phase offsets. What I want to point out here, which you will see in all my visualizations, is that I did this analysis for about a 5-month period in 2017. Each of these 5 maps shows the change that occurred within a specific time period, each of which is about a month long. Now this is the first in a series of alternative visualizations I created, the 2D maps. The units are now converted into vertical deformation in centimeters. Blue shows where the ground moved up and red where it moved down. The last map in each shows the locations of oil wells in the area too. So let's start at the top left and go through the 3 visualization subtypes and what is highlighted by each one. On the raw values maps, the whole study site is reddish for the first time period, meaning the whole ground dropped downwards, while the following maps are blue, having moved upwards. This is actually true and due mainly to different amounts of rainfall within each time period. The bluer maps had a lot more rainfall. The second subtype attempts to remove these seasonal rain effects so the localized deformation centers can be more easily seen. I created this and the next subtype using raster calculator in ArcMap. The last is cumulative deformation over time. You can see the deformation centers effectively disappear by the 3rd time period. Since the ground rebounded back upwards, the subsidence centers in the second map are effectively gone by the 3rd time step. Then I made some cross-section graphs developed using elevation data extracted in ArcMap and then graphed in Microsoft Excel, and these are my second alternative visualizations. The cross-section line from which I extracted these elevations went straight through those 2 deformation centers you saw earlier. I used the same figure subtypes as I did for the 2D maps. And here's my last visualization type, the 3D videos, which are made using ArcPro Scene and PowerPoint. You can see here how the ground appears to jump up and down in the raw value scenes because of the rainfall variations, while the difference from mean video holds relatively steady. These are realistic looking because I draped world imagery over the elevation change data. My preliminary survey evaluated all of these visualizations, included 48 responses. Most of the respondents had little to no familiarity with Densar, which is exactly what I would expect for the general population. On the right, you can see the results of my baseline question assessing how well could people interpret default interferogram images. I simply asked them if the ground in the circled area was moving up or down, and the results were a near 50-50 split. This indicated to me that the interferograms were indeed not a great option for showing this data to the public, and there was a need for alternative methods. I asked the survey takers to actually measure the magnitude of the deformation using the 2D maps and the cross-section graphs. I didn't ask them to quantify the deformation using the videos because there's no scale given on those images. In the question immediately following, I then asked them which subtype they used to make their measurements. And as you can see, most people tended to use the second visualization, which was the difference for mean subtype. This was true for both the 2D map question estimates and the cross-section question. A few people said they used a combination of the subtypes, not just one of them. In the summary of the survey, I also asked the respondents which subtype they found most understandable. The difference from average did come out on top with a cumulative deformation in second. I also asked the respondents to rate the understandability and aesthetic appeal for each of the general visualization types. The 3D videos ended up being preferred in both categories, probably because of their greater sense of realism and the lack of scale bars and numbers to figure out. So in conclusion, when trying to explain Densar measurements and geohazards, you should choose your visualization style carefully based on your purpose and your intended audience. Simplification and realism are often desirable, especially for people unfamiliar with these types of analyses. Many survey respondents commented that a combination of these visualizations would likely be most effective. And when asked which visualization type they preferred, there was a large sentiment that it depended on the question being asked, and they did not consistently prefer any one type of visualization. So overall, continued refinement of ways to visualize geohazards is important for effective communication to the public. So thank you all for coming to my presentation, and special thanks to my advisors, Jenny Mason and Danielle Smolowski, for all of their help during this project. And I'm happy to answer any questions.